kilograms. Okay, and we want to mix it with ice and melting point. So it's 0 degree ice, which is the mass is 0.15 kilograms. So finally, you are going to have some liquid water if you mix them too. And we want to, what is the final temperature of the liquid water? Okay.
Which is the same as R squared, because R equals. Yeah. If they give you a function, you just square it. And then and that's all it is.
Okay, so for this problem it's a little bit more complicated. Okay. Before you can write down the equation, you probably need to do some pre-calculation to determine what's going to happen here. Because there are two possibilities. When you mix some steam and ice with arbitrary mass, because it depends on the ratio of the two mass here. So you can think about two possibilities. One possibility is that you have a lot of steam, okay? So it will melt all the ice. So this provides heat, okay, when it goes to water, to melt all the ice. So one possibility is that you have a lot of steam, so you can melt all the ice, okay? And then the remaining heat can still raise the temperature of the water from 0 to like 10, 20, 30. Okay. Another possibility is that you have only a little bit steam. So what you have is you can only melt part of the ice. So finally you are going to get some ice-water mixture. So it really depends on this how much heat you can acquire from the steam compared with the heat needed to melt the ice. Okay. So, so to fix this issue, what we have to do, I think the best way you can do is first, you can calculate the relevant heat released from the steam, okay, and compare how much, and then calculate how much heat needed to melt the ice, okay. So you can calculate if you want to melt 0.15 kilogram heat. So basically, you want to calculate this quantity. The heat released needed to melt the ice, which is the mass, let's say this is M2, multiplied by L. Okay. Should you use F, right? So you get what? 499. Okay. So that's this number because Q2. And let's calculate, have you calculated the Q1, which is the heat released, let me put the positive side so it's easier for you. Released by the condensation process. LV. Have you calculated this quantity? Okay, so if you take the positive value, is that large?
That's a lot of joules.
Yeah.
For like 0.1 kilogram of steam.
Even if you would just still.
Maybe this.
Okay. Kilojoules. A lot of joules.
Yeah.
3 there.
I like to always convert them.
Okay, so you see, if this is the heat released from this process by changing all the 100 degree steam to 100 degree water, right? And this is heat required to melt 0 degree ice to 0 degree water. So this one is larger than this one. So that means all the ice will be melted. So after that, you can think that after this, you will get some 0 degree water, some 100 degree water here, and then they'll mix each other. Somehow the remaining heat will take them into some temperature in between. So now you can, so that will be similar to that. You have steam, 100 degrees, and water, 100 degrees.
Change temperature.
You have ice, 0 degree. Ice,
Or water, right?
water, 0 degree, and they mix with each other. So you get some water with some unknown final temperature. Here you get water with some unknown final temperature. Now, if you write down Q1, Q2, Q3, Q4, and add them together, we'll get 0 again, right? Energy is conserved if there is no energy loss. And here, similar to that one, you are going to get one equation with only one unknown number. Here, the unknown number is the final temperature. Okay. Any question here? So, if you put this, some of the number, in fact, you already calculated here. But you still need to figure out what is Q3 and Q4. They are related to the unknown temperature in final. So you can find out that. Okay? And the problem here, if you look at this part, similar to that one, but there is something you have to make sure. This is what happens. Okay, it's not another way. So you have to do that calculation to make sure finally all of them will go to water. If this number is smaller than this number, so you may get some water mixture, water ice mixture. Okay, so that's it.
So how does it change if it's a water ice mixture? How does it change the formula
if it's a water ice mixture, it's more complicated.
Then your final temperature is 0.
But then in that case, the final temperature is, yeah, it would definitely be 0. But you need, in that case, you probably want to know what fraction of the, so how much water you have, how much ice you still have. Okay.
Could be a mass ratio.
Yeah, mass ratio. That's more complicated. I guess I'm not going to make that kind of problem.
And also, in both of these two problems, we start with ice at 0 degrees and steam at 100 degrees, which leaves out, it starts us with the equation ML, the latent heat.
Okay, so here, you start with that because I give you the 100 degree steam. But if you say, I give you at another temperature, say 200 degree steam, then you have one more cube. So then before that, you may have some procedure, like say if you have steam and 200 degrees, so there is another cube. So, but again, all the cubes together should give you 0.
Yes.
Okay.
Both of those together is less than that. So does that mean your final temperature is 100?
No, because that heat should, let's see.
This is like half of the...
But what temperature here when you calculate this?
I did that for 100 temperature. This is 100.
Oh, you mean even you put 100, it's not enough to... So let's check what is...
If you do the whole formula.
Hold on, let me first check is this correct.
So we turn it all to steam? Is that what you're saying?
There'd be
2.26.
steam water mixture.
So multiply by 0.1. Okay, by the way, it seems this. You don't think so? Because you need multiply by
So that makes more sense.
0.1, right?
But steam would have more energy.
10 to the 6. So it's 2.
That's true. I can't believe that.
Okay,
Has
yeah.
that much energy.
That goes to show you how small the jewel really is, you know?
Yeah. My lord.
Or how much energy ice would
And ice almost has
This is
50,000.
It's only
So I guess it's that far.
0.5.
0 Kelvin.
Yeah. And its properties.
So let me see. Okay, I know what you mean. So here that and the 2 is still smaller than this one. Okay, so I think the problem is that I didn't check the mass. Probably I didn't give you a good mass here. I intend to make it to have final water. So let me see what mass.
Burning light smells like electrical. Right.
So if you want to make the number greater than this one, but smaller than the summation.
Or burning up or something.
It smells like rubber burning.
Yeah, like a bell.
Maybe
Someone different.
0.05.
Would be curious
Is it good enough? Let's see. If it's 0.05, so this is
Probably just don't put one in on the test.
116, and you add the two number, what do you get?
I mean, if it's taking a professor this long.
One,
Oh, they put the wrong number. It's not. It's 0.5.
Or
30.
I don't know what's going on.
Why did it go to 0.05?
Okay, so
I don't know.
that will work. Oh, no.
I'm not sure what they're actually
Yeah,
trying
because
to
this
do.
is bigger, so that'll give you a lot.
You say there, 1, 2, 3, 4, 5, 6. This is 1, 2, 3, 4, 5, 6. Okay, yeah. Okay, so, okay, for that problem, to simplify the problem, I have used 0.01 kilogram. Okay, so finally you will get some water.
You mean
In
5?
fact,
You mean 5?
0.05.
0.05 kilogram.
Yeah.
Okay. If I use 0.1 kilogram, in fact, I provide too much heat, so finally you will get the steam-water mixture, which has 100 degrees. Okay. But anyway, it's good. Now you see what happens. It depends on the ratio of the steam and the ice. If you have too much steam, so finally you get steam, water with 100, mixture with 100 degrees. If you have too much ice, you are going to get water-ice mixture at 0 degree. If in some range in between the two extreme cases, you are going to get the pure water, where the temperature can be anything between 0 to 100. Okay. So we just shift the problem, put 0.05, you are going to get water.
Should we expect a question having to deal with the final stage in a sort of multi-phase?
Okay, for this one, I think I wouldn't ask this kind of question. Here, some of the problem, okay, it's higher than the level we will require in the test. But we still need to solve this problem, because once you solve this higher level problem, you wouldn't have problem with the test. Okay. So the test, I will
Keep it in
make.
one phase.
Okay, well, I will make the number. If I make the problem like this, I will check the number carefully. So you are going to get the final water state. I will tell you, final state is purely like a pure water. Okay, no mixture like this. Okay.
What number is this?
That would be it's the third.
I thought we did 4.2. Right?
Yeah, it's the pair. That was the initial class.
Oh, okay.
Can you work out number 10?
You want me to rewrite my equation for your picture?
This one you check out.
Wait,
It just says that
What I have here is really messy.
merge.
Like, not right.
So you should have the continuity.